Yeah, okay, so thanks everyone for coming, and thanks Lexisnexis and Craig for inviting me again to do another talk. For those of you who don't know me, I am a researcher at the University of KwaZulu-Natal, and I'm currently doing my master's in something called quantum machine learning. So, can you guys hear me at the back? Good. Okay.
Yes, you can.
Great. So, quantum machine learning is just like doing machine learning on a quantum computer, which is just a different physical device than the ones we have today. So they exploit certain properties in quantum physics. But today, what I wanted to talk to you about, and because this meetup in Durban is still pretty new, I thought it would be worthwhile taking you through some of the concepts that are thrown around and taken for granted in AI, in the AI community, and one of those being neural networks, specifically artificial neural networks. So today's talk is a very, very light introduction to what this is, what they're about, and what inspired their entire designs. So they are basically inspired from biological models, so things that we have in our bodies, in our brain. And the idea is to try and create a computer, a system, a machine that kind of models these biological systems that we have. Okay, and yeah, so I mentioned that I'm part of UKZN, and then I'm also part of this startup called LearnML, which does data science education and machine learning consulting. So if you're interested, come chat to me after. And if you have any questions, just feel free to ask. So I'm going to start with just talking about the neural system of the body. So can anyone give me like a quick one-sentence definition of what they think a neural system is? And even if you don't know, if you want to guess.
Connected neurons.
And what are neurons?
With things.
Okay, good answer. Yeah, that's true. So a system of interconnected neurons. That is 100% correct. And we can think of it as our nervous system. So a neural system is the nervous system in our body, and it's like how we are able to perceive stimulus and stimuli, and then process the stimulus, and then make decisions based off of the stimulus that we receive. So for example, I can see this room through visual stimuli. My visual cortex in my brain can process what I see, and therefore send signals to my muscles and my joints, telling me how to navigate through this room so that I don't get hurt, for example. So if we break down the neural system into components, you can basically think of it as like 3 sections. So you have these things called receptors, and receptors are exactly what we receive, the stimulus that we receive. So it's the cells in your body that allow you to receive information or stimuli. And then this information is then processed by these things called neural networks. And we'll talk exactly about what that is now. And then lastly, the effectors are basically the things that take the decisions, the outputs from the neural networks, and causes you to act on them. Right? So what I mean by receptors, again, so you can think of them as like your senses, right? So, for example, your skin has thermoreceptors in them that allow you to perceive weather. So it can sense that when it's a super hot day, then your body is starting to feel hot. And so then this sends the signal, the thermoreceptor sends the signal to neural networks, which then does like some processing based on this stimulus. And finally, it sends this result, whatever that is, based on the received stimulus, to the effectors to do something. So in this example, since it's a hot day, you're feeling hot, then the effector could then say, squeeze your arm muscle to pour water over yourself, for example, to cool down. So that's just basically how a neural system kind of interacts with each other. And so in this framework of receptors, neural networks, effectors, scientists have a fairly good understanding as to how receptors work and how effectors work. But neural networks are something super complicated that we haven't really figured out yet, biological neural networks. And this is where all the decision-making happens in our brains, right? So it's natural, if we want to create a machine, a neural network, an artificial neural network, to try and model this architecture. And so this is what a biological neuron looks like. So a neuron, it was mentioned by this gentleman here in the front, and you can think about it as a basic component of something that sits in a neural network. Okay, so it's a fundamental component of a neural network, and this is a neuron. So it's like this weird-looking cell, and all you need to know here is these things at the end, these long things here, are called dendrites, and these are the receptors. These receive the stimulus from an external environment. And then some calculations happen here in the cell body. And then that sends a signal out through something called the end of the axon, the terminal of the axon. Okay, so you have some stimulus that's received through dendrites, some calculations that happen here, and then some signals based on these calculations. And obviously, if you put lots and lots of these neurons together, that's when you start forming this biological neural network, right? And some of you may be familiar with this term, synapses, so that's the transmission of signals between neurons. And obviously, again, in your brain, like, it's super, super dense. So the amount of neurons that you have, the amount of connections that you have in your brain, I think it's in the order of 10 to the 14 that we have measured. And some of our most advanced neural networks created by Google and the likes have, I think they can only run like 10 to the 11 neurons. And to do this, they need a lot of computational power. Supercomputers, tensor processing units, and so on, right? But our brains, does anyone know how much power our brains actually use? Or want to guess again? Anybody?
6% of our power,
Of?
Of our consumption of our power.
Okay, that might be true. I actually don't know. I just know that the absolute value it's 25 watts. That's enough to power a light bulb. It's ridiculously little. So we have millions of neurons, and we are powering them with the power that it takes to power a light bulb. So our brains are massively powerful supercomputers and very, very energy efficient. So when people talk about modeling the human brain, it's important to realize that we are very, very far from this kind of idea. But nevertheless, we try, right? We have to try somewhere. And so we can take this neuron and cast it into an artificial framework. And that's moving from there to here. So this is a typical picture of a neural network. You have inputs, just like you have inputs here that are received by your dendrites. And then you've got some calculations that happen here, and these things called hidden layers. And we'll unpack this as well. And then finally, you've got some output, some answer that you can then use to do something, to take an action. And that's the architecture of an artificial neural network. And you'll see, we'll go through a very simple example of the math. It's, do we feed to an artificial neural network, right? So like I said, I have visual stimuli. I can perceive you all in this room, and I can then process that information through my visual cortex, but how can a machine do this? So let's say we have black and white pictures of cats and dogs, and this task that we have is to classify whether there's a cat in the picture or a dog. Now we as humans, quite obviously, can immediately identify what's a cat and what's a dog because we have life experience, right? We have accumulated enough knowledge and information through our lives to learn what a cat is meant to look like and what a dog is meant to look like. But a machine, on the other hand, does not have this. So, again, it seems natural to then feed the machine a whole bunch of pictures of cats and dogs so that it can become good at recognizing what is meant to be a cat and what is meant to be a dog. So that is exactly what we do. We have to feed it with data and with information. By the way, this is my son Vladimir here. He asked not to be in the presentation, but I couldn't resist. And yeah, so the idea is to pump information relevant to the task that we're trying to achieve so that the machine or the algorithm or the neural network, I'm going to use these terms interchangeably, can learn patterns that exist here and pick up on trends that exist in the data. Okay? And how exactly would a machine see this image? And this is also something important to realize. So if we zoom into Vladimir's eye, for example, you can see the image starts to become very pixelized, right? Like each little block there. And what we do to convey this picture to a machine is we overlay it with numbers that represent the pixels. So if, for example, it's very dark, then the closer the pixel value to 1. If it's very light, the closer the pixel value to 0, right? So this is mostly white, so that's 0. These are all very dark. And you do this for the entire image. And so you end up with like these large grids of numbers. This is called a matrix in mathematics. And that's what you feed into the computer. So you've got lots of these matrices, these large grids of numbers, which you feed into the computer so that it can start to pick up on trends and patterns that we can't see as humans. Okay, everybody good? Okay, cool. Yeah, so now it figures out these patterns. So when we feed it in new pictures, it can then say, okay, this is what the grid of numbers looks like, and based on the patterns that I've figured out, that's a cat and that's a dog. And that's the idea of a neural network. And obviously, you can then start to feed in any kinds of pictures, right? So not just cats and dogs, but pictures of cars, of fruits, of people, of any animals. And what you're looking at here is predictions by a neural network. Very good one. So at the top, you've got the word, the prediction for what's in the picture, and then the next most likely prediction thereafter. So for example, here the neural network's predicted a leopard, but it's also saying that it might be a jaguar, it might be a cheetah, a snow leopard, and so on. Here it's predicted a cherry, and then the next highest prediction is Dalmatian. So you can see it's quite good at like picking up multiple things in an image, right? And then we can start to generalize to videos. So neural networks can classify pictures very well, and videos are just still images, right? In a timestamp. So if we start to feed it video imaging, then you can start to classify things in real time and through videos. So here what you're seeing is a computer vision or neural network that's classifying things that it's seeing while driving. So it's saying that's another car, that's a traffic light, truck, car, and so on. And a friend of mine created this startup where in South Africa, what they have, so they use the video camera images at taxi ranks to count how many people are entering taxis and exiting taxis. And this is quite important, right? Because taxis are very well known for overloading and it can be very dangerous. And they said that they once found a taxi that was authorized to load 14 people and it had close to 70 children in it. So obviously this is a very bad thing. So it's like interesting applications of this kind of work that we can do here in South Africa. And since neural networks are very good at recognizing patterns and trends, right? They don't just have to classify things, they can also produce images, they can also create things. So what you're looking at here are two people that don't exist. These pictures were completely generated by neural networks, based on thousands of pictures that were fed to it of people that do exist. So it picked up on trends and features, and now we can specify to generate people within certain age groups, and it gets down to amazing detail, high definition quality. And just to highlight how amazing this is, if we just look 5 years ago, we couldn't even simulate an image that had color. And this quite clearly looks like someone that's fake. And in 3 years, thanks to the advancement of neural networks, specifically generative adversarial neural networks, for those who want to know the specifics, that's the kind of quality that we're getting. And soon we'll be able to start simulating very high quality video, which can be very exciting for like games and virtual reality, but can also be kind of scary, right? Okay, so it's important to know that these neural networks, they do things based on the data and the information that we feed them. And they're very, very sensitive to the data and the information that we feed them. So what you're looking at here is a word cloud from social media. So this is representative of what women use very frequently when they post stuff on social media, right? The bigger the word, the more frequent it is amongst females. So you can see they like saying things like shopping, excited, love you. So if we had to create a neural network that would speak like a woman through social media, it's very likely that it's going to use this kind of language. And then when we look at a male, you can see now that it's very likely that this neural network is going to produce something that swears a lot, that talks about black ops and games. I'm surprised to see my wife made it there. But yeah, very different, right? And because it's very sensitive to the information we feed it, it can also go very wrong. So I don't know if you guys at the back can see the labels here, but can anyone tell me what's wrong with this? So this is meant to predict what sport is being played in the picture, right? So here it's got basketball, 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 ping pong, baseball, rugby, ping pong. This neural network is clearly very racist, right? Because nobody is even playing basketball here, but all the black players are classified as basketball players. All the Chinese players are ping pong players, yet this guy's clearly playing soccer, and this guy's, I don't know, weightlifting or something. And so this is a clear example of how neural networks can be biased to the information that we train on. So we need to be cognizant of that, and we need to be aware that we shouldn't just trust all these things blindly. This is a Google search I did yesterday of beautiful woman, right? Can anyone tell me what's wrong with this picture? Yes. Must be blonde.
Yeah.
Is that what you noticed? How about the fact that they're mostly white and they all have long hair? Right? They all have long hair. So like a neural network has learned based on tagged pictures to classify beautiful women as women with long hair and as white women. Again, very sensitive to the information, the labeled information that we feed it. Whereas if you do a beautiful woman in South Africa, the reverse happens. Now there's only black women and a lot with short hair. So these things are very fickle, and we need to be careful of that when we start to train them and code them up. Okay, so that is it with examples. Now we go through the math of building a very, very simple neural network, and then that's it from me. We'll take some questions at this time. Okay, and all right, so let's build one. Okay, so suppose we have this problem where we've got a grayscale picture, and in it, we want to classify if there's a mountain or not. Okay, so it's just a very random example, and let's say our picture looks like this. So we have some picture, and when we zoom into it, we only have 4 pixels, very simple. So we can convert these pixels into numbers, right? So remember I said the darker the pixel, the closer it is to 1. And if it's light, then it's close to 0. So these are our values for our 4 pixels. And we can kind of stretch this thing out and write it like this. And these can serve as the inputs that we feed into our neural network. Okay, so our input layer is what we call it. And so this is representing the picture that we have. And what we want to get to is our output layer, an output that tells us whether this is a mountain or not, if there's a mountain in that picture or not. So in this example, I'm just going to say 1, the answer of 1 represents a mountain, the answer of 0 represents no mountain in the picture, okay? And we can think of this structure again as the biological neuron. We're receiving some input stimulus, and we want to come out with some outputs, and then we need to do some mathematical calculations here in the middle. And this is what we call in machine learning, in neural networks, the hidden layer. Okay, so a hidden layer, we can specify the architecture. We can say how many nodes do we want in the hidden layer, how many hidden layers we want, and it can get very complicated. But just for a very simple example, let's assume we have 1 hidden layer, and we have 3 nodes in the hidden layer. Okay? And so now we have to find a way to connect our dendrites, our inputs, into the cell body so that some calculations can happen. And we do that by something called weights. Okay? So we connect each input to each node by a weight. And these lines represent the weights. And all a weight is a number. Okay? It's just a number. I'm just going to write it as W1, W2, W3, W4, but they're just 4 numbers. Okay, we don't know what they are yet. And to calculate the value of this node here in the input layer, it's a very, very simple function. It's a linear function. You're just taking the first one times your first number plus the second one times your second number plus the third one times your third number, fourth one times your fourth number. So I'm ignoring a few subtleties here. There are like some, for those of you who are quite technical, there's like an activation function and a bias that I'm leaving out. But this is all you really need to understand. This is all that's happening in a neural network, is you're taking your weights and you're connecting them to your inputs, and that's what's happening in the nodes. Okay? And then you do this again. So you've got 4 different numbers here connecting this node. And then you do it again for the third one. Okay? And I'm just going to say that I'm going to choose random numbers for all the W's, and I'm just going to say we get these results for these nodes. Cool, so that's the results of our hidden layer. And then we want to get to our prediction of 0 and 1. Is there a mountain? Is there not? And so we do exactly the same thing again. And then we end up with some number here that will give us an indication as to whether there is a mountain or not in this picture. And that's, again, also equal to a linear combination of the numbers. And let's say it's equal to 1, so there is a mountain in this picture. Okay, so now we have, I spoke about all these weights, right? So there were 4 weights for this node, 4 for this one, 4 for this one, and 3 for this one. Now, in a neural network, we don't know what those weights are. And the whole idea behind, the whole genius behind neural networks is it figures out a way to learn these weights, such that if you feed it any kind of picture, it can make a very good prediction. And that's, so like, training the neural network means learning what these weights are, what these values are. And that's all there is to it. If we, by the way, if we had to add another hidden layer in this architecture, that's what we call deep learning. Okay, so how do we do that? How do we train the neural network? Well, then we have to feed it a whole bunch of pictures that contain mountains and that don't contain mountains, right? So that it can then learn the patterns like it did with the cat example and the dog example. So we feed it a whole bunch of images and we say, these ones have mountains in them and these ones don't. So that it can go through this architecture, guess the values here and here, check it against the answer, was it right or not, and then go back and update it such that it can make better predictions the next time. And that's what you call training the neural network. Cool. Any questions about that? Of a mountain, for those of you who can't see at the back, and we're represented by these numbers, then it goes through really like good mathematical mappings now because we know what those weights are and get the right prediction. And if we had to put in like pictures of clouds, then it should say no mountain. Cool. We can talk about different types of neural networks, as I spoke specifically about image recognition, but they're also good at like language processing and a whole bunch of things which require different architectures. But it's important to know that they're very sensitive to data. Okay, so they can be very biased, like we pointed out. And we're still very far from approximating things like the human brain, from artificial general intelligence, the things that scare people, still very far away. But neural networks are very, very good at certain tasks. In fact, better than us at many. One of those being like cancer cell recognition, for example. So a neural network can now identify cancer cells, pictures, with almost 100% accuracy. And the field is still very new, so even though neural networks have been around for decades, machine learning in general is still very new and there's a lot to be explored. And yeah, I left out quite a few important concepts, but if you're interested in this stuff, I do encourage you to read up further, and these are some really, really nice resources that you can look at. So I'll put the slides up in the Meetup group, so you don't have to worry about taking these down, but this is very cool, this neural network playground. So Google's TensorFlow, they've come up with this website where you can play around with different data sets and create and build your own neural networks and check out how accurate they are. It's very nice. And then of course, if you like coding, scikit-learn is like this library where you can easily do machine learning, and the documentation is awesome. And this is probably one of the best books to read, deep learning. And I have to credit the slides to my supervisor because most of it was from her, Dr. Maria Schultz, but she's not here tonight. And yeah, thanks. That's it.
How does it learn? How
does it learn? Okay, that's a very good question. So I just kind of casually said it goes back and updates the weights, right?
Yeah.
Like it iterates through. But there are clever ways to mathematically do that. So there's something called a cost function, where it essentially calculates what your answers are meant to be and what the answers actually are. So the neural network will predict answers for you, right? Predict labels for the images. And then you know what the labels are meant to be, right? So a cost function checks these two. And it says, did the neural network get it right? Yes. Okay, cool. If it didn't, no. And the cost function is then a mathematical function that gets minimized based on these values for W. So it's quite mathematical, but essentially what you're doing is, and there's different ways to do it. So there's things called like gradient descent, which calculate the gradient of this cost function. And then you're trying to like minimize this cost function. If there was a whiteboard here, I would draw it, and then it's quite nice. But you can think of it as like, this cost function is like some curve, right? And you want to minimize it. You want your neural network and the answers to be as close as possible. So you find the values for W that minimize this curve, that like gives you the very bottom point on this curve. So, and we fortunately don't have to worry too much about it because Google and a lot of people have coded up very nice frameworks, software frameworks for this. So you can literally just say cost function equals this, and run it through some code, and it will minimize your cost function for you. So yeah, did I just confuse you more?
So it's like a variation, so you're trying to minimize the variation from...
Yeah, exactly, yes. The variation between what your answer should be and what the neural network is saying, minimizing that mathematically. Cool. Yeah?
So when we have a quantum computer eventually one day, like a practical quantum computer, will it significantly speed up or empower this artificial neural network?
No. Not this one, no. So a quantum computer, you can't do things like stochastic gradient descent and such because you can't do backpropagation, right? So a quantum neural network is a different architecture to the classical one. But in terms of speedups and exponential speedups, you will definitely get benefits in certain implementations of certain algorithms. So like in support vector machines, which doesn't need, I'm just assuming you're familiar with machine learning, right? Okay, so in support vector machines, which don't rely on backpropagation and updating these weights, they use things like kernel functions, which map your data to high dimensions, right? Now, in a quantum computer, this happens naturally. So you have like exponential speedups that happen in SVMs on a quantum computer, whereas a neural network can't even really be formulated well in this setting. So, and also I have to say the caveat is there's so much we don't know about quantum computing, and there's so much we don't know about machine learning. So, stand to be corrected in the future, but at the moment, yeah. So no speed up for a neural network. yeah.
And also your knowledge of quantum computing. You say, because I've heard a theory once that there's a theory that the brain is actually done like a type of quantum computer, or modeling like a real neural network with a quantum computer. Because also this thing of modeling physical things with quantum computers would be, the chemicals, chemical modeling.
Yeah, it's actually quite a beautiful idea. So 100% right, and the answer is we have no idea how the brain works.
Yes.
But we do know that the brain does exhibit some certain quantum properties, and it's very, very cool because if you look at certain elements, so let's take lithium for example. So lithium is used as an antidepressant, and it has chemical effects on the brain. And if you look at the atomic structure of lithium and you change the quantum effects, the atomic structure is still the same, but the quantum effects are different. And when you do that, lithium has an entirely different effect on your brain. So they tested this on rats, and the mother rats immediately stopped caring about their young when you change the quantum properties of lithium. Yet the atomic structure is the same. So to us, without looking at quantum, it looks exactly the same. So, and also nobody has figured out how consciousness works. So this has also, of course, ties to quantum physics. And nobody knows how anesthesia really works because it cuts off your consciousness. And it's believed that there are quantum properties in the brain that cause the switch on, switch off effect. So yeah, it's very interesting. We actually have a quantum biologist in our group who's looking at this kind of work. So it's very cool. Yeah. By the way, we have positions open for students who want to join our group, a master's, PhD, so if you're interested, please do contact me. Okay, cool. Thanks, guys.
Once again, welcome to everybody. It's a Monday and it's the start of the school year, so really, really good that this many people turned out, right? So I'm Leon, I'm the dev manager upstairs. So it tells you two things. I'm in management, one. Two, I'm not a machine learning expert, and I'm not a mathematician in any way. I used to be a programmer, still write lots of code, but what happened in the last meetup is that we found that there were lots of people here that were lay people and programmers who wanted to get into machine learning and AI, right? People that didn't necessarily know lots about it but wanted to learn about it. But this is a talk for them, right? It's not going to be highly advanced, it's not going to be super clever, but if you want to start dabbling in machine learning. Okay, so we're going to talk about machine learning and we're going to talk about an algorithm called linear regression. And it's the easiest, I think it's the easiest machine learning algorithm, right? If you were to go to one of the machine learning courses on one of the MOOCs, this is the first thing they teach you. They teach you linear regression. Because the maths is fairly easy and the implementations are fairly easy, right? Okay, so let's start with this. What's machine learning? Okay, this is the easy stuff. A machine is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks T as measured by P improves with the experience E. And if you do some partial derivatives and formula below, you'll be able to do the linear regression. What? Okay, so this is not that talk. I'm not going to talk about how the calculus works. Right? If you don't understand what WAP means, right? And if you still don't understand what WAP means, it's WAP, right? So let's go with that. Okay. So I'm not going to talk about the maths, right? It's not that the maths isn't important. It's that for most of our common everyday problems, like for me trying to work out whether one of my clients is going to cancel, you need an intuitive understanding rather than a deep understanding, right? And unfortunately, and I feel this, because I'm a compiler person, right? And I like compilers, and like my favorite compiler course got cancelled. It's structure interpretation of computer programs, because the lecturers didn't believe people needed to know that level of detail anymore, right? And it's the same for machine learning. For 10 years ago, you needed to know the maths. You need to know it deeply. You don't need to know it anymore. You need to understand it intuitively, and maybe a little bit on some of the easier stuff, okay? So you can probably get by without knowing too much of the maths, right? So anyway, so this is a talk about machine learning. So instead I'm going to talk about my personal life, right? So I married my high school girlfriend, right? And before that, she was my best friend for like 5 years before that, right? So there's now 3 groups of people in this room. There's the romantics, and they think, oh, that's so sweet. Bless you. There's the other people that are thinking, oh my God, what a loser, one girl. Right? And you are there as well. And then there's my internet people, and they're thinking this. And the follow-up to that is this. Is it possible to learn this problem? No, it is not. There's some randomness involved in how I got all the friends on, so can't teach this. But anyway, let's get back to the topic. Okay. So I'm going to tell you. So the reason I brought up my wife is because I'm going to tell you a story. Because I was in the friend zone, the first fight we had was like 6 months into our relationship, because I had to make sure that I still kept. So we had this massive fight. I don't remember what it was about, right? And I had no experience of this whatsoever, right? So it was a campus. I go to campus in the morning and I do this thing. I tried my first strategy. I pretended like nothing had happened the day before, right? And right, so I got that. That was the expression that I got, right? Didn't work. About lunchtime, so we were sitting at one of these desks in the cafeteria. I know how to make origami, so I made her an origami parrot, put it next to her, and she almost smiled. Right? And I knew now I was in, right? So I made her another one, and this time I drew on it, and then I was definitely in. And by the end of the day, we're back to that, right? So I'm telling you it's a story for a reason, right? It's because I was in a situation that I didn't understand, that I needed to learn about, right? And here's how it worked, right? I gathered the available data. At the beginning, there was nothing, so my strategy was to do nothing, right? I used the available data to form an improved hypothesis of what I was going to do, an improved plan of action, right? And that was basically to do nothing, right? I performed that action, I gathered the resulting data. The resulting data said nothing had changed and things had actually gotten worse, right? Then I tried something new that had based on the input, right? And that's how machine learning works, right? It's a 3-step thing: perception, cognition, and actions, right? And yeah, that's pretty much it, right? That's how neural networks work. Okay, and not neural networks. Wrong talk. That's how most machine learning algorithms work, right? So if you go to one of the online MOOCs, I think even either the Udacity one or the Coursera one, they'll talk about it very much in this pattern of speaking, right? But anyway, let's go back to this, right? So this is a talk about machine learning. So instead, I'm going to talk about my personal life again. right? Okay, so I hurt my neck over the weekend, so I was a little bit on painkillers when I was making this talk. Right? So I thought, what if I could mathematically figure out how long my wife would stay angry after a fight, right? And so that's the problem we're going to solve. We're going to solve how long it takes my wife to forgive me for whatever stupid thing I've done, right? And so the first step in any of this, and this is like data science, right? First step is collect some data, right? So I took her the attributes of fights and I put it into a table. So her arms crossed, is she like doing this thing, right? That tells whether she's really angry. Has she said the word fine? How many times has she said the word fine? Right? Did she contact her best friend? Because that's a problem, right? Were they crying and how many minutes of it? What was my level of stupidity in this argument? How stupid was I, right? Length of the argument, maximum volume reached, was my mother-in-law consulted, and if you take all these factors together, you can calculate this thing at the bottom, time in the dog box. Right? And that's what we're going to try and calculate today. Right? We're going to try and calculate that today. And we're going to use linear regression, and we're going to use an algorithm called gradient descent. Right? So let's get into some of the... So, the other side, because it's taking too a while. If you were to take one of those variables, like, for example, how loud the argument was, and you were to plot it on a line, and you were to then plot it a line against time in the dog box, which is the thing we're trying to predict, you'd have all these points that sit above the ideal trend line, right? And to be able to learn and to go through that process of gathering data, perceiving, and then acting, you have to be able to work out the error of where you are. So if you make a little hypothesis, and you have to be able to calculate how wrong you are. Once you can calculate how wrong you are, you can then make a better hypothesis. So the first thing to be able to do is to be able to work out how wrong you are. So in linear regression, because it's so simple, you do squared errors, right? So you work out the difference between that point and that point in the line, that point in the line, and you do a square for those. We use a square because, one, it stays positive, and two, you want to penalize values further away from the line, right? Right? And so that's what Amira was talking about. You get, and that's our cost function, right? Now the cost function has a curve of its own, right? And this diagram shows exactly what you're trying to do with the curve. So at the initial point of the algorithm, when we start by guessing a set of values for coefficients of the line, the cost function's values are out here. We're trying to get it to go here, right? So to be able to do this work, you need to be able to do two things. You need to be able to do a little bit of calculus and a little bit of linear algebra. Not too much though for this algorithm, right? So you start off like this. Conceptually, you guess a line, right? My guess was really bad. And you work out the cost, and the cost function says this is where you are, right? And then once you can measure the line, you can measure the slope. And what you want to be able to do is go down the slope. It's like trying to find the lowest point, right? Do an improved hypothesis. The balls move from here to here. The line looks better, right? And magically, we did this in 3 steps. But at the end of it all, you're at the very bottom of the line. It's what you call convergence of the algorithm, where the changes in each iteration is so small that it's almost pointless to keep going, right? Okay, so that's all I'm going to say about at this from a PowerPoint perspective, right? So what we're going to do now is we're going to look at the actual code involved in it. Right? So I've got a little Jupyter notebook, and I'll display it. Okay, so bear with me while I try and figure this stuff out, because I'm like an old person with the broken. Okay, cool. So the point of this lecture is to see how easy this is, right? And it's for people who want to go dabble. Like you go home and you think like, I'm going to work out how long it takes my pet to eat food every day, and I've got some factors I'll calculate, right? So first first thing to do is import some libraries. So the things we're going to use is C1, which is visualization. That sits into something called Matplotlib, which it'll make you draw graphs. It lets you draw pictures. That's about it, right? There's pandas. Now, because I'm a compiler person, as I said, I love pandas because it's a column-oriented data store and it's got its own domain-specific language. Don't worry. I had to say it because I love that kind of stuff, right? Okay, so the first thing we want to do is get the data, right? So what I did was, I spent the last 3 months fighting with my wife, like just picking random arguments so that I could get data, so that I could do this stuff, right? Because that's what you do in the name of science. so we have the CSV. Maybe I'll show you the original quickly so that you can see the data. That is why my neck is sore. Yes. See if I can get the data. Okay. So that's what the data looks like, right? Arms crossed, best friend consulted, mother-in-law consulted, my level of stupidity, comma separated list of values. Easy peasy, right? So pandas will read this into a data set. It will read it into a column-oriented in-memory store, and which means you can start working with it, right? So if I print the top of it, I see this is the data that I put in just to prove that it actually got in there. I'm not actually going to run it now because I've had Death by Live demo before. I won't do it again, right? Okay, so if you're going to be playing in this machine learning world, the algorithms are complicated. Don't get me wrong, right? They're super complicated, but for me anyway. But knowing your data, knowing your domain is about as important, if not more so, right? Being able to understand the problem yourself before throwing. So it's like this: you can't expect the machine to understand the problem if you can't, right? Well, not yet anyway, right? So understanding and visualizing, seeing the problem, super important, right? So what we're doing here is visualizing the data, right? So this is a plot of the number of times she said the word fine versus the time I spent in the dog box. So you see, it's kind of a line. There's some kind of correlation if you want to look for it. And then length of arc immersion versus time in the dog box here. Also, some kind of correlation. Okay, so here's the point I want to focus on. So, whether my mother-in-law was consulted or not, you know, if they ever hear this talk, they're going to kill me. It's going to be like death. But anyway, there's an X here. Like, what the hell is up with that? Why is there an X there? So, in the real world, whenever we're dealing with data, the data is never clean. Right? This is like relatively clean data. Half of the problem is cleaning the data versus actually running the algorithms. So, the next little bit is a very trivial way of cleaning up the data. So in pandas, you can map a function onto, you can map a map onto a function. It's pretty clever. So I'm saying if you find an x, make it 0, and then plot the graphic, right? And now you can see there's only yeses and nos, really. Right? And that's the other thing. The machines don't really like text, so you want to make the text into numbers. There's some libraries that do this. Like if you're playing, there's a thing called one-hot encoder, which sits in the same family of algorithms that will do this kind of stuff for you, but I did it manually. Okay, so more visualization. Skip. Just for the purposes of this, you could do it all in one go. If you can ask Python to visualize all the data for you in one go, and you can see the plots between each variable and each other variable. Personally, I prefer doing one-by-one. I get confused easily, so this doesn't really work for me. Okay, so next step that I followed was I did a correlation between the various columns in my data set, right? And you can see, so this is the map of the correlations. Darker colors mean more correlated, lighter colors mean less correlated, right? What's amusing is this, that obviously I didn't really pick fights with my wife for 3 months, right? I randomly generated the data in Excel, and still my levels of stupidity won, because that's the most correlated item in the thing. It's like pretty incredible. It's like Excel knew me better than I knew myself. Oh, no. Okay, right. So I visualized the data, right? I decided that the word find, so I picked a data set of data to work with, the length of the argument, those 4 values. I said those are the 4 values I'm gonna run this algorithm over, right? So I'm gonna try and explain overfitting and testing and training data. Right? You can't use, for a machine learning algorithm to be good, you need to be able to train it on some data and test it on other data, right? And given that I have a small set of data, like 50 rows or whatever it is, there's a library in Python that will take your training data and split it up into training and testing values, right? So what you want to do is train the data against known values and test it against unknown values, and then you can see if the data is any good, because the way these algorithms will work is that it will try and fit the data you give it, right? It always works for the data you give it to train with, because that's how you're training it, right? Which is why, it's a weird example, but UK did a pawn filter, a massive pawn filter on their so if you're in the UK, you have to opt in for pawn, right? But it couldn't figure out the difference between humans and pictures of deserts, because deserts have okay, let's not carry on with this. This is why you should prepare for it. Like, this is why you prepare for a talk, right? You don't do it the night before. You need to edit that out. Okay, so next step is to split the data between for a training set and a testing set, and now I've got 4 sets of values. So x, in this world, y is the value I'm trying to predict, and x is all the factors that are going to try and predict y, right? So y is time in the dog box, x is everything else, right? And for somebody that's hacking around like me, this is what is, we're almost there, right? We're about at the end of it. So I printed some data out just for my own sanity to make sure that this thing has split the data correctly. So running linear regression in Python is as simple as this. You 2 lines, right? You create a new linear regression object, and you tell it to fit the data you have. There's far more complicated ways. There's far more options available, right? But in the very, very basic case, the basic case of I want to learn something, it's 2 lines, right? And then, so what does it calculate? So what it does is it calculates the coefficients of the line, right? And so this is what it's telling me, right? The length of time that my wife will stay angry at me is 0.6 times whether her arms were crossed, 0.21 times how many times she said the word fine, and 3.96 times my level of stupidity. So obviously, once again, confirms my level of stupidity is the winner in all these things, right? But nonetheless, that's it, right? So we can do some other things after this. Okay, so we can run we can take the values that I predicted and the values that exist in the data set and plot them against each other, right? And this is the result of that. And in a perfect world, it's probably to be 145-degree line, right? But that's against the training set. So I used random data, so this model didn't fit particularly well, right? And then you run the same plot against the testing data. And once again, I can see some trend there. But that's it. That's linear regression for beginners. One last thing, you can get a score from the model, and that score just tells you how good the model is. I think mine is like 0.7 or something, which is kind of okay, I guess. But that's it. That's one last thing. I'm going to go back to my PowerPoint. Okay, so the online, the MOOCs that are fairly good at it is, you can see a few courses here. There's a course on linear algebra for machine learning, right? Lots of machine learning is just lots of linear algebra, right? And it gives, once again, it gives you an intuitive understanding of linear algebra, not a very deep one. But it's like a 5-week course and it's pretty trivial. Then there's an equivalent calculus course that exists in Coursera. So these 3 courses form one thing that you can pay for, but you don't actually have to pay for any of them. You just kind of do that. And then this YouTube channel, which I absolutely love. I think it's 3 brown, 1 blue. Sky.
3 blue, 1 brown.
3 brown, yeah, 3 blue, 1 brown. And Sky has the most amazing way of explaining maths. His introduction to linear algebra and also calculus are really, really good. So if you're like me and you don't really get it, he's the guy you want to listen to. Right? And that's it. Thank you.
I know you wanted to speak about bias and variance, but you never mentioned the fact, or you didn't include in your data set the fact that your wife might have done something wrong. Why didn't you do that?
When has she ever done anything?
Okay.
Last thing, I'm going to go home, right? I'm going to tell her about this talk, and then she's going to have a fight with me. And then I'm going to come back at the next meetup and tell you if I actually predicted how long it would last, right? And if that works, then I'm going to quit and I'm just going to become a machine learning expert.
Good evening. My name is Edgar Quaira, and I'm very pleased that Craig invited me back to give the second component of this talk. Just to give you an idea of what my planned trajectory is here. Last time we met, I spoke about sort of the elementary details of Spark, basically a little bit about what Spark actually is and the fundamental data structure for Spark, which is the RDD. Today, I'm going to be talking about data frames in Spark, and this basically takes the unstructured way of handling data that we spoke about last time with RDDs and moves to a structured way, so a tabular way of storing data. And then the plan for next time, should I be fortunate to be invited back again, will be to talk about how we can now take our data in tabular format and then build machine learning models on top of that. And for those of you who were not here last time and don't have an idea of what Spark is all about, it's basically a system for doing analytics on large quantities of data where you take that data and you distribute it across multiple computers operating in a network. Okay, so the old paradigm, or the original paradigm with Spark, was the RDDs, and it started off with you initiating a connection to Spark by creating a Spark context. So that's the way we created this handle to interact with Spark last time. Now, as Spark evolved, the idea was to go from this unstructured way of dealing with data to a more structured way. Data frames entered the picture, and it was necessary to build sort of a different and more sophisticated way to interact with the cluster. And this is where the idea of a Spark session evolved. So we're now going to leave behind the idea of a Spark context and create a Spark session. That's going to give us some additional ways of interacting with the cluster. So starting off your interaction with Spark, you create the Spark session object. And as you're going to see, we're going to use this object for creating other structures that we're going to use for managing our data. Okay, now I mentioned that we're going to be talking about data in a structured format, and this means that basically we're going to be reading in data and putting it into a table. So we're aiming to transform our data into a structure in which it has a whole bunch of rows or records, and each of these rows would correspond to a particular observation, and you'll be seeing many examples of those a little bit later on. And the columns in the table, well, these are the individual fields or the characteristics of each of those observations. And the typical sort of name for these in R and Python and Spark is a data frame. Data frame is synonymous with the table. So we're going to start off by looking at how you can create a data frame from first principles. So in reality, it's very unlikely that you would ever do this, because normally your data is going to come from a CSV file or an API or a database query. But it's really handy for your understanding to know how these things are actually constructed from scratch. And so what you're going to see is that there are actually a number of ways in which you can create a simple data frame. So I realized that I've kind of jumped a little bit ahead of myself. I'm indebted to Leon for introducing the Jupyter Notebooks. I'm also working in the Jupyter Notebook, and the language that I'm using for interaction here, much the same way as Leon was, is Python. So I'm going to kick off by creating my first data frame. It's going to be based on a Python list, on an array. And this array is going to be called people, and it has 4 elements. So 1, 2, 3, 4. Each of those elements is a tuple, which is just another data structure in Python. And each of those tuples has 3 elements. A number, which you're going to see as simply an identifier, followed by a name, followed by another number, which for argument's sake we're going to just assume as an age. Right? This is going to be stored in a variable called people, and if we take a look at the contents of people, then we see it's just this long sequence of tuples. Now, we're going to take that and move it across from Python into Spark. And we do that using that Spark session object that we created earlier. It has a method called createDataFrame, and this createDataFrame method actually will consume data in a variety of different formats, one of which is a Python list. So the first argument to this method is people, so the data that we've just created. We provide it with the second argument, the schema. This is just a set of labels for the columns or the fields in our data frame. So we're specifying the first column is going to be called ID, then name, and then age. And the result that we get back is a data frame. Now this is not particularly informative because I want to actually see that data frame. And we'll see in just a moment how we can visualize that data frame once it's in Spark. But before we do that, we're going to look at some other ways of creating a data frame in Spark. We spent a lot of time in the last session looking at RDDs, and it's perfectly feasible to go directly from an RDD across to a data frame, provided that your data in the RDD is kind of conformant to this tabular structure so that you can break it down into rows and columns. So to illustrate this point, what I'm going to do is run this SC parallelize, which you'll recall from last time is something that just takes a Python data structure and essentially spreads it out across the cluster, immediately giving you an RDD. So the result from this parallelize method is an RDD, and that's now being consumed by the createDataFrame method. And you once again end up with a data frame object. The third way that I'm going to show you for creating a data frame in Spark is directly from a pandas data frame. Now, Leon also very conveniently mentioned pandas. Pandas is the library in Python for handling tabular data. And what I'm going to do as a starting point is to take my list of data, so this is a fundamental Python list, and transform it into a pandas data frame, and take immediately take a look at that, and this is the representation of that pandas data frame in a Jupyter notebook, and it's very nice and neat. You can't see it in the projector, but it's actually very nicely displayed with alternating light and dark rows. It's the presentation of a pandas data frame in a Jupyter notebook is really very pleasing, and we can now take that pandas data frame and transform it immediately into a Spark data frame, once again by calling precisely the same method. So this method is very nice in the sense that it consumes data in a variety of different formats. Okay, so we've now got our data in a Spark data frame called people, and we'd like to take a look at it and have some sort of a view very much like the view that we had with the pandas data frame. The method that allows us to do that is called show. So people, the name of our data frame, .show, will give us a view on what that data frame looks like inside Spark, and we see exactly the same thing now. A column for ID, column for name, and a column for age. Right. That's how you would get to a data frame if you were doing things from scratch. But of course, in reality, you would never really do that. So you'd pull your data through from some other source of significant data. I mean, for a start, it wouldn't make sense to use Spark to process a data frame with only 4 rows. That would be completely absurd. So what we're going to do is look at this attribute of the Spark session object called read. And this attribute is actually it's an object of this data frame reader class. And this reader class has a bunch of methods, each of which allows you to consume data from a different source. These are the methods, so there's a CSV, JSON, Parquet, JDBC, and text. And we'll be talking about all of them except for the last one. So let's start off with looking at how data would come in from the CSV file. So this is the source that Leon's data was in as well. So it was a file consisting of a bunch of rows, and within each of those rows you had fields, and the fields were separated by a comma. Okay, so the C in the CSV is for comma, but CSV has become sort of like a global catch-all term for any kind of delimited file. So the delimiter between fields need not be a comma, it might be a semicolon or a pipe or a hash or any one of those things. We're going to try and consume some data from a CSV file directly into Spark, and this is what the file looks like. Again, super small and simple file for illustration purposes. It's got 3 records. The first of them is a header record, right? That gives the names of the columns. So we've got name, age, and job. And then we've got 2 records. And if you can see, then you will note that the separators, the delimiters here are not commas, but they're semicolons. So we're going to have to tell Spark, hold on, if you're expecting a comma, actually you need to be looking for a semicolon. Now the way we go about consuming that into Spark is to call the .csv method. And the first argument to that method is where do we find this data? So it's going to be the path to the location of the file. So it's located in my data folder. There's the name of the file, developers.csv. And we provide it with some other information that tells us the specifics about what that data looks like. So we know that it's not really a CSV file, it's actually a semicolon delimited file. So we specify that the separator between fields is actually a semicolon. And the final argument here, header equals true. Well, this tells Spark that it can actually get the names of the columns for the data frame directly from the data itself. And you can see that the result, when we call the show method, is a nice tabular representation of precisely this data. Spark has identified the column names, and those have from the first record of the file. And then we've got the 2 records with the data. So this is a very typical way of getting data into Spark. Normally, you wouldn't have the enormous data file sitting on your laptop or even on a server. Most likely, it's going to be the column is null, so indicating that as far as Spark is concerned, those data are missing. Okay, so CSV, very common data format, but in the internet age, JSON is also an extremely common format for transferring data, especially if the data are unstructured. So Spark has the ability to consume JSON data as well. So for example, if this is what your JSON data file looks like, you just run the JSON method and it will consume that very beautifully and produce a data frame for you. Now, I mentioned initially that these data frames are aimed to handle structured data, and this is largely true. You're aiming to have a single value per column, but it's not necessarily the case. If you have unstructured data, for example, in a JSON, and what will happen is that one of the columns in your data frame, as we'll see in just a moment, will end up containing a vector or a list. In fact, the very next example has precisely that. So the next data format that we're going to look at is Parquet. Now, as opposed to JSON and CSV, Parquet is actually a binary format, so it's not meaningful.
And
you
want you want a float?
I beg your pardon?
Floats instead, so it just makes everything integers, right?
Not everything. So you can see that the size ends up being a double.
Yeah.
So that's because it has a decimal.
And the one at the end that comes something. Oh, that's also a double.
It's also a double. Yeah.
Okay.
So Spark will try and do the right thing regarding data types.
What is a double?
A double is what?
Very close.
Is it a float? And what type of float, right?
Single precision, I think. Well, no, double precision, so that makes it what? 16.
64? Okay.
16 bytes. 8 bytes? 8 bytes. 64 bits.
You're the programmer.
No, I'm not. I'm a physicist, but I think we can confirm that 8 bytes are 64 bits. So, yeah. So that's single precision.
Thank you.
Cool. Okay. So, thanks.
No, I should know this too.
No, I think that you and I can have the same excuse. I'm merely a physicist. Okay, so Parquet, it's a binary data format actually developed originally for the Hadoop ecosystem. And what's nice about Parquet is that it's column-oriented, and this principal benefit from my perspective of column-oriented data is that you can actually compress it very effectively because the data type along an entire column is always going to be the same, so you can apply the same sort of approach to compressing those data rather than row-oriented data where your data type is changing from one field to another. Anyway, this is becoming quite a pervasive format for data in the Spark ecosystem, and we can see an example here of reading data in from a Parquet file where this favorite numbers column actually contains vectors or lists. So here, this is not really structured data as such because within that single column, you've got multiple values. Okay, probably the most interesting source of data for Spark, though, is actually executing a query against a database. And for that, you've got this JDBC method. And to make this work, you need to provide a little bit of information. So, for example, you need to tell Spark what driver to use because it needs to know what kind of database it's interacting with. And in this case, just to keep things simple, I'm using a SQLite database, which means it's just a local file on my computer. But in principle, Spark can interact with pretty much any database for which there is a driver. You also need to tell it a couple of elementary things like, where is this database? Now, for SQLite, it's simply a case of giving the path, so where that database resides on my computer. So here I give the path to the database file, and then the table that we're going to be querying. So we're looking at this file called flights.db, and we're pulling out a table called flights. And this is then going to be fed into Spark by chaining all of these things together, giving all of those various options as option arguments, and then finally calling the load method and ending up with data in a nice table. And this works very, very nicely across a variety of databases. It's certainly the most common way that we like to get our data into Spark. Okay, so presuming now that we've got our data into the cluster, what can we do with it? Well, the first thing we can do is take a look at a couple of the attributes of the data frame. So it's got this columns attribute, which just gives you a list of the column names. The data types, we've seen that before, so which types are assigned to each of those columns. And then there's this RDD attribute, which allows you to go from the data frame back to the RDD if you need to or want to. What about methods? Well, there are a whole host of these. In fact, the documentation for the data frame class in Spark is extremely extensive. So I've just picked out a couple of more useful ones. The first question that I always ask of a data set is, once I know the number of columns, is how many rows? Because this gives you an idea of just exactly how much data you're talking about. So the count method will give you back the number of rows. So we see in our people data set, there are only 4 rows. We've seen the show method already. So this, in principle, will show you the data frame. But of course, if your data frame is really large, you don't want to see all of it, right? You want to see just a subset. And the show method will, by default, just show you the first 20 records or less if there are less than 20 records in your data frame. And as we'll see presently, you can actually specify how many records you want to see explicitly as well. Okay. There's also this collect method and the 2pandas method. Now, the collect method is quite, it's interesting, I guess, but it's potentially dangerous. What collect does is essentially goes across the entire cluster, grabs all the data and pulls it back to a single node so that you can take a look at it, which is great for precisely this purpose, that is looking at what the data looks like inside Spark. What we can see is that the data frame is actually made up of a sequence of these row objects, right? So these 4 row objects, and it's these row objects that are being distributed across the cluster. So for example, if you have a cluster with 2 nodes, you might expect there to be 2 rows on the one and 2 rows on the other. Of course, in reality, you have a lot more data. There's going to be a lot more data on each of the individual nodes. And you've also got this 2pandas method, which takes your Spark data frame and converts it into a pandas data frame. And this is very handy if you've done some analysis in Spark and then you now want to do some local post-processing on your machine, and you're more comfortable doing that in pandas. So then being able to flip across to pandas is very, very handy. Both of these methods do have a downside, and that is that they literally go and get all of the data from the entire cluster. And if that data set is really, really large, it's going to A, take a lot of time, and B, when all that data arrives on your machine and it's unable to cope with that volume of data, it's not going to work out well. Okay. Right, so let's talk about a couple of operations on these data frames. We've seen how we can just get a global view of what the data looks like. Now we're going to see how we can kind of slice and dice these data, because this is going to be the first step towards preparing the data for building a machine learning model. So we're going to look initially at things that we can do with columns, and then things that we can do with rows. And the standard operations that you're doing with columns are, well, mutating the columns, so taking the existing columns and applying some sort of operation to them. We're probably not going to talk about that today. The other thing is selecting columns. So you've got a data frame with a whole bunch of different columns, and you only want a subset of those. So we're aiming initially to look at that. We can address individual columns within a data frame in 2 ways. The one is to simply treat them as an attribute. So for example, if we want to pick out the name column from the people data frame, simply people.name, accessing that. It's as if it was a Python attribute. The other is to use the square brackets operator and provide the quoted name of the column. Both of those give you precisely the same thing. Here you see that the result that's returned to you is a column object, okay, as opposed to a row object. But normally you don't want to have this column object. You want to get back a data frame. So a better approach to pulling out one or more columns is to use this select method. So if you call select, you provide it with the names of one or more columns. So for example, selecting the name column, this gives us back a data frame with just a single column. And if we want to take a look at the results of that, call the show method on it. So people, pull out a particular column and then show me what it looks like. You can see there that we just get the single name column from the data frame. And if we want to have multiple columns, well then we just string together multiple column names. And of course you can use this for reordering your columns as well. So for example, if you want your final result to have the name column before the ID column, you just list them in precisely that order. Okay, so that's about the column-wise operations. What about row-wise? Well, normally the row-wise operations that I'm applying are take this entire data set and give me just a subset of the data according to some sort of logical condition. And there are a couple of ways that we can go about doing this, all of which rely on this method called filter. And filter accepts as its single argument a logical predicate, so something that gives you back a series of Boolean values, and what it's going to return to you is only those records from the data frame for which that predicate is true. So for example, here, the predicate is people.age greater than 25, so this is comparing the age column in my people data frame to 25, and it's going to return true if the age is greater than 25 and false otherwise. And then finally show the results, and we see that from our data frame of 4 records, we get back only those which have an age greater than 25. Now, it's possible to take these predicates and string them together, because normally you don't just have one condition that you're wanting to apply, you have multiple conditions. So what you can do is you can apply multiple filter operations in succession, so you can filter on one condition and then filter on another and another and another. Alternatively, you can also try and bin all these conditions within a single filter operation. So for example, here we have taken people greater than 25 and ORed those together with people whose names is Andrew. Michael. I'm obviously very self-obsessed. Okay, and so the result is that we get back sort of the older people and Michael as well. Of course, this approach is really useful because this allows you to do an OR operation. If you're simply stringing together filters, what you're doing is ANDing. So you're saying, apply this operation, and this operation, and this operation. Whereas here, you can essentially use any kind of Boolean operation to combine those different conditions. The final, and probably from my perspective, most useful way of doing filtering is to apply or supply a SQL-based condition. So anything that you can use in a where clause in SQL, you can insert as the argument to filter. So this is saying, give me back the records where age is greater than 25 or name is Michael. This would work perfectly in a SQL query on the same data set as well. So if you're comfortable with SQL, then this is definitely the best way to filter out a sequence of records from your data set. Okay. So the final operation that I want to talk about is how we can take data from multiple tables and merge them together. And this is handy, especially if you've pulled your data in from the database and you've essentially mirrored a couple of tables and you're now wanting to merge them together. The way we go about doing this is using the join method, and you can see that it has quite a bit of flexibility. There are a few arguments that you can supply to it, but essentially the fundamental things are you need to tell it what's the data frame on the left, what's the data frame on the right, and what operation is being applied when you merge them together. So to illustrate this, we've got 2 data frames that we loaded in earlier. So we've got the employees data and we've got the people data, and what we're going to do is very simply merge those together, and we're going to apply the merge by simply matching on the name column. So we're going to use the name column as the common column between the 2 data sets. And the way that we go about doing this is we have the table on the left. On that we call the join method, provide the name of the table on the right. Then we specify how those 2 tables are being joined together. So in other words, how the rows are going to be compared in order to make that merge. And then the type of join. And as you may have seen before, Spark sort of supports the kinds of joins that you would expect if you come from a SQL background. So inner, left or right, outer joins, full join. It also has this left semi and left anti, which I don't think actually exists in a SQL database. They do exist in R, they may exist in Pandas as well, but they're super handy in the sense that, so what the left semi-join does is it gives you back all the records from the table on the left that have a match in the table on the right. But the table on the right is not actually included in the results. It's basically just used as a filter. And the left anti gives you back everything in the table on the left that isn't matched in the table on the right. So deployer in R has precisely these verbs. So they end up being really, really handy if you're using data sets to filter other data sets. So that's essentially the core of what I wanted to tell you about working with structured data in Spark. I know that there's a lot of information here, and I'll definitely provide you with the notebooks so that you can consume this in your own time. The good news is that next time, if I'm invited back, we'll speak about something a little bit more interesting, and that is how we can take all of this stuff now and actually build some machine learning models in principle on a big chunk of data.
I've got one. Just around, so this is almost mirror-like to pandas, right? If you sort of understand pandas, you can sort of make your way around Spark. Setting indexes and group bys and the sort of things that you can do in pandas, is that all possible within Spark?
I think most of the functionality that you'll find to deal with data frames and pandas is mirrored in Spark. Okay. Yeah. As I said, the documentation for the data frame in Spark is huge. There's an enormous amount of functionality associated with it.
And then just further up, we had the RX7 with the NA, and you had null values equals NA. What happens if you have like N-A or N/A? Do you have to cater for every single one of those, or how would you clean something like that? That's
a good question. I'm not actually sure. I think that the argument that you specify for null values is interpreted as a literal string. Okay. It would be really nice if it was interpreted as a regular expression, for example, but I don't think it is. Okay. But to be honest, I'm not sure. I would hope that it was a regular expression, but I don't think so. Okay. Yes?
Yeah. Can you do, does it do a query push down if you have like a complicated long, vehicles and then filter calls to the database? Because obviously the database can do that filtering better than taking all the one table, taking another table, and joining it up in Spark.
Yes, it does, and you can actually visualize that because evaluation in Spark is lazy. You can actually string together a sequence of operations and then visualize what that's going to look like when it's pushed through the database. So, I mean, it tries to take advantage of the fact that all of the operations are lazily evaluated.
You mentioned unstructured data, you want to do JSON. Would you say Spark is well suited to unstructured text data in large volumes, or something else work better?
So you can very definitely do text data in Spark. But I mean, I guess it depends on what exactly you're wanting to do with it. If you're wanting to build a classifier, then you're probably going to build a term document matrix or something like that. Ultimately, you're going to be taking your data set, which is unstructured, and enforcing some sort of structure upon it, and then building a model. So what happened on my machine was it started swapping vigorously, and then I basically couldn't do anything, and then ended up having to reboot. Because, I mean, it fills up your RAM, and then it tries to take whatever doesn't fit into RAM and swap it out disk, and then it gets to a point where you run out of disk space, and then it's got nowhere to go. American.
Okay, so correct me if I say anything wrong. So the RDD object, I'm still not so I don't have a full understanding of this. So if you have a very big data set, and then you want to process that data set, then you can, let's say you have 2 clusters running. So it splits the object and then processes them in parallel on both clusters, right? Mm-hmm. Okay, so if one cluster fails, then the full object is recovered here. That's the key.
That's the principle. That's the resilient in the RDD.
Yeah, right? And so then, does it store like a very compressed version of the full data set across the nodes, across the clusters?
It doesn't really store, store the copy of the data, but what it does know is how to regenerate those data, because it's got it knows, like, you started off with this, and then you applied these operations to end up with this next RDD. And I think that the reason that works well is that your RDDs are immutable. So you can't have an RDD and then modify it. It's got to be, every new RDD is derived from another one.
Okay, so this must be some low-level, like, functional programming thing that I don't understand, right?
I would guess so.
Thank you.
Because
So you remember last time I spoke about that expensive shuffling operation
Yes.
when data gets moved around from one node to another? So that's what's going to happen. If there's like a serious mismatch and you're performing a join, then there's going to be a lot of shuffling of data back and forth between nodes.
okay.
Because, I mean, remember that your data frame ultimately consists of rows, and it's the rows that are going to be distributed across your cluster. Now, if you're taking two data frames and you're merging them together, what you're essentially doing is taking, like, let's say, a row from that node and a row from that node and squishing them together to form a new row that's then going to be stored on one or the other. So data is definitely going to have to move back and forth over the network. So in principle, your join operation is going to be an expensive one.
Yeah, can't do it once.
Yeah, exactly. Or like do it in the database
Yeah.
to mitigate things happening on the cluster.